Hello and welcome to a short video where I'm going to run through the simulation for exercise 5 in this introduction to Solidworks Simulation. So exercise 5 we're looking at a cast aluminium bracket here, and we want to simulate how the bracket would behave if it's loaded and kind of placed in bending. So for a bit of context, what we're kind of comparing this to, or what we're trying to simulate in effect, is if this bracket was bolted down to a rigid surface, like it's bolted onto a machine or a base plate or something like that. But rather than modelling all of the parts and the fasteners and applying our forces and see how the actual components interact, we can simulate some of that using just the model of the bracket itself, and by careful use of fixtures we can model how the bracket would bend. So in the brief here, in the document on the Moodle page, I've set it up to run 3 studies, kind of getting progressively better. There's the first one here using a fixed geometry fixture. We'll see is not very accurate. It's not really how the model would behave in the real world, bolted to a surface like that. The second one, where we apply fixture to the bolt holes themselves, is probably a little bit better, but again we'll see it's not particularly accurate. And then in the third study we'll look at a better way of doing it. Okay, so I'll run quickly through the first 2 studies. So we go to the simulation tab and create a new study. Static simulation. And we're going to, I'll start off with the mesh. We'll just use the default mesh parameters to begin with. So the default mesh parameters here is a 6mm mesh. Through that, and it's taking a little minute to mesh this. There is a slight issue with some of the geometry here. Is a little bit difficult to mesh. Just where that cylinder meets the rib at the bottom here does give some very, I suppose, a tight little corner here that's difficult for the meshing algorithm to work upon. But most of the stresses and deflections that we're interested in are going to happen down around the bolt holes and maybe underneath the bottom of the rib here. So I think that's okay. Right, so for the first study we're just going to do a very, very simple fixed geometry fixture applied to the bottom surface of the part. We're going to apply a force, so right click on loads here, we're going to apply a normal force, so perpendicular to that circular surface back here, of 1200 newtons. Okay, and that's it for study 1. It's very simple, very simplistic, I suppose you could say. We're just treating this as if the entire bottom surface was fixed to the plate. So if we run that study, would be fairly quick to run, and we can see, if we look in at the side of it here, this is going to place the bracket in bending. All of the bending is happening in this back flange here. The bottom surface stays completely stuck to where it was originally. What I find useful for these result plots is to right click on the result plot and go to settings, and we'll turn on the option where you can overlay or superimpose the model shape, so the original shape of the part and the deformed shape of the part displayed together. Okay, so you kind of see a ghost image of the original shape of the part and the deformed shape. Now bear in mind this is very much exaggerated by a factor of 445 in this case. We'll do the same thing for the displacement plot. Go to settings and turn on the ghost image of the model shape. Okay, so for study 1, where the entire bottom surface is fixed to the ground, if you like, or fixed to that base plate, we're getting a displacement of 3 by 10 to the minus 2 millimeters. Okay, so what we're trying to simulate, as I said, is this bracket if it was fixed to a base plate. Now, in that kind of a scenario, the back of the base plate would be free to lift up off the back of the bracket, would be free to lift up off the base plate, and it's just been held in place by these bolts and washers here. So that study there, study 1, static 1, is probably not very realistic, that it kind of assumes that the entire bottom surface is fixed to the base plate, which in reality it's not. Okay, but it gives us some first approximation of how the bracket would bend. Okay, so what we'll do is we'll duplicate this. We'll right click on your study static 1. We'll create a copy of that called static 2. And what that's going to do is it's create a new study that has the same material properties, the same mesh, the same forces. But what we'll do is we'll change the fixtures here. So I'm going to delete the old fixture. And this time I'm going to apply, again, just a fixed geometry fixture, but I'm going to apply it to the cylindrical surface of the bolt holes here. So the inner surface here. Okay, and that's it. That's the only change I'm making for the second one. We'll run the study again. Okay, and if we look at the results of the second study, we can see that it's probably a little bit more realistic to the loading situation and the fixtures with the bolts and washers here. So we can see that the back of the bracket is free to lift up here, as it would be in reality. So we get some bending happening in this bottom flange, as well as bending happening along the back of the bracket here. So that's probably a little bit more realistic. It's still not perfect in that if we look here, we can see that the front of this flange here underneath the rib is free to push down, whereas in reality this would be sitting on top of a rigid steel base plate and it wouldn't be free to actually push down. Okay, but it is an improvement on the first study. The displacement results here will be probably a little bit more realistic. It's about maybe 3 times the displacement we had in the last one. But as I said, yeah, it's still not perfect. So we'll do another study here, study 3, static 3. I'm going to create again a duplicate of this. So right click, copy study to create a duplicate again. We'll call this just static 3. So in static 3, what we're going to do is we're going to try and more accurately represent what's happening here. So we want something to represent this rigid steel base plate, and we want some way of representing what's happening here with the bolts and the washers. So to represent the steel base plate, what we're going to do is we're going to use something called a virtual wall. And to represent the bolts and the washers, what I'm going to do is create a split line feature to create an area on the top of this flange to represent, so we can apply fixtures to represent those bolts and washers. I might do that first. So back in the model tab here again, I'm going to create a split line feature on surrounding those 2 holes to represent the washers. So the first thing I'll do is I'll create a sketch on that top surface here, and that sketch is simply going to be 2 circles that are concentric with these holes. I'll create a circle, concentric with that hole, and a circle concentric with this hole over here. Okay, and they'll be diameter. The circles, I want them to be diameter 20. And this one I don't think is concentric. So I'll add a concentric relation here. Okay, so at the moment that sketch isn't doing anything, it's just sitting there on that plane. What I want to do now is take that sketch, sketch 13, and I'm going to go to Features, Curves, and Split Line here. So I'll use that sketch 13 as the basis for a split line feature. So we're going to do a projection where we project sketch 13 onto these areas here, so face 1 and face 2. And what that'll do is anywhere where that sketch intersects with those faces, it'll divide them up into separate areas. Once I click OK here, that now is divided up into 2 separate areas here and 2 separate areas over here. So in my simulation study, I can apply fixtures to that region to represent what's happening with the washers. Delete the old fixture out of here. So we want to apply one type of fixture to represent the washers, and then we'll apply another fixture to stop the whole model from sliding around in the X and Z directions. So under fixtures, there's a number of ways you could do this. The easiest one would be the roller slider fixture, but I'll just maybe have a look at some of the other ones as well. Do the exact same thing. So we could use a reference geometry fixture like we've used in the past. Say, take this area and prevent it from moving in a particular direction. We can use the on flat faces fixture, which again does the same thing. We could take face 1 and prevent it from moving perpendicular to itself. So that would stop the washer faces from moving up and down in the stop the washer faces from moving up and down perpendicular to themselves. And that's exactly what the roller slider fixture would do as well. It would take those areas and prevent them from moving perpendicular to themselves. Okay, so that's like your bolt and your washer going down screwed into a threaded hole or something. Would prevent this from lifting up in the Y direction. Okay. So you could either use a roller slider or a non-flat faces command, saying with no perpendicular movement. It's the exact same thing. To stop the bolt holes themselves from moving about in the X and Z directions, we're going to use, right click here, go to Advanced Fixtures. We're going to use a type of fixture that's, again, kind of like the reference geometry fixture, but it's specifically set up for cylindrical faces. So this time we'll use the on cylindrical faces fixture applied to those 2 cylinders. And similar to the reference geometry, you can define what components of movement you want to restrict. So you can restrict the axial movement, so that would be up and down in the Y direction. You can restrict the radial movement, that would be to stop these cylinders from expanding or contracting in the radial directions, which might work, but would also stop the holes from flexing as they're under stress. So instead what we'll do is we'll restrict the circumferential movement of these holes, so that would stop them from moving about any angular displacement. So we'll set the displacement to 0 radians of angular displacement here, and that'll effectively stop those stop the holes from moving about in the X and Z directions, but it'll leave them free to flex, to expand and contract. Okay, so that should effectively simulate the bolts and the washers. To simulate the rigid steel base plate that this thing is going to be bolted down to, we're going to use a different type of entity that'll act like a fixture, but it's not, strictly speaking, it's not a fixture. What we want to do is we want to create a virtual surface or a virtual wall that this part can sit down onto. That it'll be free to lift off of this virtual surface, but it won't be free to penetrate down into it. Okay, and effectively what we're going to be doing is creating a virtual copy, like a virtual component, and then define a connection between our bracket and this virtual component. So if we were doing a simulation of the entire model with the steel plate and the bolts and the washers and everything, we would have to define a connection between the bracket and the steel plate, like a type of contact connection that says this part is free to lift up off the steel plate, but it's not free to penetrate down into the steel plate. We'll be doing something very similar to that, but using a virtual wall instead. So the way you apply that is in your study here, we're going to go to connections rather than fixtures. We're going to connections, and we're going to define a local interaction between the bottom surface of the part and this virtual wall here. So the type of connection here, we're going to change that from contact. We're going to change it to a virtual wall connection. And we're going to apply that to the bottom surface of our part. And we're going to, here in this purple box, we need to select a plane, a plane that we're fixing that bottom surface to. Or, that the bottom surface will be coincident with, maybe better. So we could either create a plane that's coincident with the bottom surface, but in this case we actually already have a plane coincident there. We have this top plane of the model. So we're saying we're going to use this top plane as a virtual wall that the bottom surface of the bracket can't push down through it, but it is free to lift up off of it. And click OK. So you see the virtual wall then appears here in our list of fixtures, even though we actually created it here under connections. And that should be the model more or less ready to run. The last thing we might want to do is, we could create a mesh here. Excuse me, sorry. We could create our mesh the same as before, but what I'd like to do before running the model though is I'd like to refine the mesh a little bit. We already know we're going to have fairly high stresses around the bolt holes. We saw that from static 2. And we also know that we're going to have kind of stresses around about where the rib meets this flange down at the bottom here. There's compressive stresses. And we have some tensile stresses at the back here as well. Also, there's a slight issue with the geometry, the way it meets, the way this cylinder meets that rib there. It meets at a very sharp corner. So I'd like to refine the mesh a little bit before running it. So what we'll do is we'll apply some mesh controls like we've seen in previous exercises. So here under mesh, before we run the meshing algorithm, before we run it again, I suppose, we'll apply a mesh control here. So I'm going to apply a mesh control to the bolt holes and the washer faces, and say any elements that are touching those surfaces, we want those to have a smaller element edge length. I'm going to set that about 1.0 millimeters. Okay. We'll do the same. We'll create a mesh control. Apply a mesh control to, let's say, this front surface of this here. We'll have any elements along here, we'll have a finer mesh. And also anything directly touching those, so the elements kind of directly underneath that will be affected by that mesh control as well. And likewise, any elements that are touching that edge of that face up here should be finer as well. We could maybe add the mesh control to this line, or this line over here, but I think this should be fine as it is. So we'll apply again, 1 millimeter again should be fine. So now when we run the meshing algorithm, any elements touching any of those faces or those edges should be finer. But we still want the overall global mesh parameter to be reasonably coarse, about 6 millimeters again. Might take a little bit longer to run the meshing algorithm this time. Let's see. Okay, you see then that the elements directly touching the areas where we had the mesh control are much finer, but also the elements in a region surrounding that are slightly finer as well. Likewise, the elements directly touching the front of that web are quite fine, but also the elements directly adjacent to that area are kind of fine as well. And likewise up here, the elements touching or kind of adjacent to that face are a bit finer, so we should have a better quality mesh in that region there. Okay, so that I think that was set up and ready to run. We have our two fixtures simulating the bolts and washers. We have our virtual wall down at the bottom here to stop the part penetrating down into that, but allowing it free to lift up from it. Okay, so I'm going to run the simulation at that. I might pause the video because it might take a little bit longer to run this simulation. Okay, so that just took about a minute to run. It does take a little bit longer to run the simulation with the virtual wall in there because it has to simulate all the contact between the nodes of the model and this virtual wall here. So it's a little bit more complex of a calculation than just the part on its own. I'm just going to turn off the display of those fixtures and stuff here as well. Okay, so these are our results for the third simulation. We're getting von Mises stress up to about 58 megapascals around the hole. A little bit lower here, probably again compressive stress around here. You can see that the bottom edge of the front here has not penetrated down into the virtual wall, but you can actually see that the top surface of the flange here has pushed down, kind of under compression from this front web here. You can see the kind of pattern of stress around about the washer face as well. So the part it's bending up. This flange here is bending up, but it's not being allowed to lift up at the washer contact area here. So you're getting kind of stresses around about that region there. Okay. So I think this is probably a reasonably good approximation of how the bolt and washer bolting this thing down to a rigid surface would actually behave here. So in terms of displacements, we're getting about 0.1 of a millimeter roughly. So again, this is exaggerated deformation here. In terms of von Mises stress, I said up to about 58 megapascal around the bolt hole. We can right click on that and use the probe tool to see we're getting maybe about 28 megapascals down here under that web, about 23, 24 megapascals in the web itself, and then probably tensile stresses back here, but they're smaller, kind of 2 megapascals, something like that. Now, von Mises stress doesn't tell you whether those are tensile or compressive stresses, or what the directions of those stresses would be either. It is useful to say, there's a lot of stress around the bolt holes, there's a medium amount of stress in this region, but it doesn't tell you whether they're tensile or compressive stresses, and it doesn't tell you the direction of those stresses either. So what I asked for in the Word document, give me a second. What I asked for in the Word document was some stresses, some results plots rather. We have our 3 default values here, von Mises, displacement and strain, but I also want vector plots of the principal stresses. So they tell you whether it is tensile or compressive and what direction, more important. And finally, the last thing I want to do is I want to look, say, at the shear stresses on the plane perpendicular to the rib. This is just for an example, but basically I want to create a coordinate system lined up with this rib so that I can look at normal stresses or shear stresses or whatever, but in a particular orientation within that part. Okay, so I'm going to create a new stress plot where I look at the principal stresses. So the first principal stress. There we go. So change from von Mises stress, I'm going to look at the first principal stress. But rather than a colored contour plot, I'm going to check the box for a vector plot here. Now, what that excuse me, what the first principal stress will show me is the maximum normal stress. It might be hard to see on screen here, but you'll see in your own example that you can see, if you zoom in a little bit, you'll see on the back of the part here, it's under tension, which is more or less vertical in the y direction. So that would be kind of bending stresses on the back of the part. If we look around the bolt holes, there are regions of tension and there's regions of compression, but it'll be whatever the maximum normal stress is at any particular location in the part. That's the first principal stress. So it kind of tells you where the part is in tension and what direction that tension runs in, more importantly. So the first principal stress is the maximum normal stress. We'll create another stress plot looking at the second principal stress, again as a vector plot. And the second principal stress will be at 90 degrees to the first principal stress. And we'll do the third one as well. The third principal stress tends to be the usually compressive stresses, so the minimum, if you like, the largest negative stress, the largest compressive stress usually. Go third principal stress as a vector plot. And I'd expect to see kind of this region at the front of the rib here would be probably in compression. Again, maybe hard to see on screen here, but there's arrows running more or less aligned with the that rib running down the front of the part here. You have compressive stresses running more or less vertically or aligned with that. In the region directly underneath that rib, then they're running pretty much vertically in the y direction here. Okay, so those are your third principal stresses, tends to be the maximum compressive stresses on the part. You'll see around the bolt hole and around the washer area here as well, there's regions in compression, and it shows you the direction of that stress as well. Okay, now the default value that you'd be familiar with looking at is von Mises stress, and really what von Mises stress is it combines those three principal stresses into one number. So it combines all the tensile and compressive and really all the shear stresses as well into a single number, but doesn't tell you whether they're tensile or compressive. So sometimes it's useful to get maybe the first and third principal stresses. You can also look at von Mises stress as what's called a tensor plot, which shows you those tensile and compressive vectors combined together. So we might do that as well. We look at von Mises stress, but under advanced options we'll show it as a tensor plot. So that kind of shows you for a particular region of your graph, it shows you the three principal stresses. We can only see two of them here because it's in plane stress. There's almost zero stress in the third direction there when you're looking at the front surface of that part. If we were to look in here, maybe you can see, yeah, we can just about see there's three principal stresses. The largest is that third principal stress, the compressive one. There are also two others at 90 degrees to that. If we look around the surface of the hole, it's a bit more obvious here. So we'll see that there's the largest stress is that third principal stress in compression. This would be the first principal stress, the maximum tensile stress. And then the third one going at 90 degrees to that is your second principal stress here. Okay, you can see this one as well. You've got actually three compressive stresses. Your first, second and third are all compressive in that location. Okay, so that's just another representation of von Mises stress. It kind of shows you that von Mises stress is made up of three principal stresses combined together with each other at a particular location. Okay. Yeah, so that's von Mises stress as a tensor plot. The last thing I'd asked for in the document though was to look at some of the stresses in orientation aligned with this rib here. So to do that, there's a couple of ways you could do it, but I think it's a useful exercise in itself to create a coordinate system to do that. We go back to the model tab here. I want to create a new coordinate system that's lined up with this rib. So back in the model tab, I'm going to create a feature. I'm going to go to reference geometry and I'm going to create a new coordinate system. We could do this using planes and that, but I'm going to create a coordinate system. So when you're creating a coordinate system, there's two parts to that. The first is the position of the origin, and the second part is the orientation. If all you're doing is looking at stresses and that, the position of the origin really doesn't matter. It doesn't affect the directions. But what I will do is I'll just place the origin here at the bottom of the rib. It doesn't functionally affect any of the stresses or anything, but we'll put it there. Excuse me. So yeah, the location of the origin is the first part. The second part, and the more important part here, is the orientation of that. There's a couple of ways we could do it. So if I want my y-axis to line up with this rib, so the y-axis is the green one here, I could either say, I could manually put in the angle here if I knew it, but I don't know it. I could say I want the y-axis to line up with an edge here, so something that runs in the direction I want. Or I could also say, let's say I want the z-axis, the blue one here, to come perpendicularly out of that face. So I could say under the z-axis here, click that face, and that z-axis is now perpendicular to that face. Alternatively, I could say I want the y-axis to line up with one of these edges here. That's 180 degrees away from where I want it. So I'll flip the direction of it with these two arrows here. Okay, so that coordinate system now is lined up with my rib. I'll click OK at that. Okay, so yeah, I now have a new coordinate system there. And I can use that then in my studies to look at results relative to that coordinate system. So if I create a new stress plot, I can look at any of the normal stresses, x, y, z, relative to that new coordinate system. Shear stresses relative to the new coordinate system, or principal stresses won't be affected because they're independent of the coordinate system. So let's say if I looked at sigma y, under advanced options, then I can select coordinate system 2 here, and that'll be sigma y relative to my new y-axis. Okay. What I asked for in the document, I think, was the shear stress perpendicular to this web, or this rib. So it's going to be one of these three here: tau xy, tau xz, or tau yz. So relative to my new coordinate system, I don't know how well you can make that out on screen there, but so let's say a plane perpendicular to that, like the cross section, if you like, of that rib, would be the xz plane. This plane here. If this is x here, this is z. So what I want is the shear stress on the xz plane. And it's the shear stress in the z direction on the xz plane. Remember that z direction is the one perpendicular to this rib. So this is the one I want here, is the shear stress in the z direction on the xz plane, where it's tau yz. So tau, if you imagine a little element of material, we're looking at the shear stress on the y side of that element in the z direction. Okay, and that is the shear stress in that orientation. So along the rib there, that would be actually very low. It's almost zero perpendicular to that rib there. But if you come back a little bit away from that, it's about 2 megapascals there. 3.5 megapascals there. So it's like shear stress in bending, where the shear stress is zero at the surface, but it gets bigger as you go away from the surface. Okay, so I'm going to finish up the video with that. it's run on quite a bit longer than intended, but I'm sure you'll be able to pause and rewind sections that are relevant to your own simulation studies. Okay, so thanks for watching.